One issue that often arises in calculating probability is counting the number of items in the sample space and listing maybe the items in the sample space. And we want to talk about some techniques for doing those things. One technique is called a tree diagram, and we can set up a tree diagram like this. An example is worth a lot of explanation. Suppose we're talking about flipping a coin and rolling a die, and we want to make a tree diagram of that situation. We establish a starting point and then think about the first idea, the notion of flipping a coin. What are the possibilities? Well, we can get a head or a tail. So we go off from that starting point and we establish the position for head and tail. And now, what about the second item, rolling a die? Well, from that point, we could roll either a 1, 2, 3, 4, 5, or 6. And we could do the same thing for tail, 1 through 6. Now, with the tree diagram, several things are possible. We could list our sample space in a way like this. We have here, the end of this tree, the end of this branch is a 1, but it came from right here, the head, so we have head 1. So this is really H1, and this one represents H2, and then H3, and then so on all the way down to the bottom. And from looking at the tree diagram, we can easily see that there are 12 items in the sample space, and we can list those items here. We can give them sort of a name or a label if we go down another column like this. Okay, suppose we take the same idea, but we roll the die first. Roll the die, then flip the coin. Well, it's the same idea. We have a starting point, and we think about the first thing that we're going to do, the first part or the first experiment. Rolling the die means we come up with 6 different possibilities. So we go to these 6 different positions and we label them. And then the next part is to flip a coin. So from each of these numbers, we go out and we have 2 choices. So it's head or tails. And now once again, we could label, this is the position of 1 head. You see, and a comma might work out here. No comma, that's fine. Whatever kind of notation you want to use is okay. This is 1 and then tail. And then this is 2 and then head. And 2 and then tail, and so on. So we would have another list of all of them. Suppose we want to make the tree diagram. We're going to go with a tree diagram from the beginning now and show how the tree diagram takes shape. Suppose we're talking about 3 tennis matches and we want to list all of the win-loss sequences involved. Well, we would start, and for the first match, we would either have a win or a loss. Those are all of the possibilities. So at this point, this is where we are with at the end of the first match. Now, what's possible after that? Well, whether we have won or lost the first match, in the second match, we could either win or lose. So, let's see, from here, then, we have the possibility of a win or a loss. And from here, we have the possibility of a win or a loss. And at this point, we have finished our second match. Now, what about the third match? Well, after we have won this match, after we have played 2 matches, whether we have won or lost, we have the opportunity to either win or lose the third match. So from each of these points, we go out and we offer those choices. Win, loss. Win, loss. Win, loss. And my tree is not real pretty, but from here now we can write the sequence that gets us to the outer part of each of these branches and list all of the possible sequences, the win-loss sequences for the group of 3 matches. So here, how did we get to this point? Well, we got to this point with a WWW. So it's win, win, win. for match 1, 2, and 3. And I don't have quite enough room here to label the third match, but I would presumably do that. But now where are we here? Well, we get here from win-win-loss. And then to this point, it's win-loss-win. And to this point, win-loss-loss. And then down here, we have a win, but we started out with a loss over here, so it's loss-win-win. You see, and then here, loss-win-lose. And then lose-lose-win. And then lose-lose-lose. And let's hope that doesn't occur. But at any rate, these are all the possible sequences by looking at the tree diagram. We see that if we're talking about what's the probability of one of these, we can count here and see that we have 1, 2, 3, 4, 5, 6, 7, 8 items in the sample space, so we could actually write a probability here if we thought that all of these items were equally likely to occur. Suppose we have, and this is a little bit different than the previous problems. Suppose there are 5 balls in an urn. They're all the same size, but there are different colored balls involved. 3 of them are red, 2 of them are blue. Now we want to write the possible sequences when we draw 2 balls, and we're not going to replace the first one without replacement. And we want to calculate probabilities for each of those sequences. Okay, so when we reach in the urn the first time, remember 3 red balls, 2 blue ones. So what are the possibilities? What can we draw out of there? A snake? No! We draw out a ball and it's colored either red or blue. So we have these 2 choices. Now these choices have associated with them a probability, and we can write the probabilities here along our branches. The red, there are 3 red and 2 blue. There's a total of 5 balls. If 3 of them are red and they all have an equal chance of being drawn, then the probability of drawing the red is 3 out of 5. The probability of drawing a blue, if there are only 2 blues out of the 5, then the probability of drawing a blue is 2 out of 5. Okay, now after we have drawn one of these balls and set it aside, thrown it away, there are now 4 balls left in the urn. And what are our possibilities then for drawing the next ball? Well, after a red ball has been drawn, then one of these reds is not in there. There are only 2 reds left and 2 blues. All right, so the possibility, though, still exists that we can draw a red ball or a blue ball. So after drawing red, we could draw another red, or we could draw blue. And after we've drawn a blue ball, after we've drawn one of these blues, there's still a blue left in there, so we could still possibly draw a blue. So after we've drawn a blue, we could draw either a red or a blue. Now, what about probabilities? Let's think about that. See, at this point, we have already drawn a red ball, and so at this point there are only 2 reds and 2 blues. Now what's the probability at that point, given that the first ball was red, what's the probability that the next ball is going to be red? Well, let's see. If we've got at this point we have 2 reds, 2 blues, so we have 2 out of 4 is the probability of drawing another red. Now, after that red is drawn, what's the probability of drawing blue? Well, it's 2 and 2, you see, so it's 2 out of 4 as well. All right, let's come down here. What if the first ball drawn was a blue? That's what this implies. So the blue is gone, and now what's left in the urn is 3 reds, 1 blue. So 3 red. I could even make a note of that. 3 reds, 1 blue. So what's the probability then of drawing red if I've got 3 reds and 1 blue? I've got a total of 4 balls. 3 of them are red, so it's 3 out of 4. and the probability of blue would be 1 out of the 4. Now, what about the probability of these various sequences? The probability of red, red, the probability of red, blue, the probability of blue, red, the probability of blue, blue. Well, we can figure that rather easily now that we have gone through and thought carefully about each of the separate probabilities at all stages of the event. We can now simply multiply probabilities. That is, the probability of red, red is the probability of red times the probability of red on the second ball. And the probability of red on the first one, I'm looking back over, it was 3 out of 5. And on the second one, it was, let me look back over here. Oh yes, here it is, 2 out of 4. So it's 3/5 times 2/4. And back over here, 2/4. You know, to be technically correct, I ought to say that this is red given red. Given that red occurred on the first one, what's the probability of red on the second one? That's what we're really calculating here. All right, we have a little cancellation. This is 1/2. 1/2 times 3/5 turns out to be 3/10. And then for the next one, the probability of red, then blue, is the probability of red times the probability of blue given red. And we just look over at the chart. The probability of red here is 3/5. We know that pretty much. But the probability of blue given red, let's come back over here. So blue given red, what's the blue? All right, that's the 2/4. All right, back over here. So we have 2/4 once again. And that also turns out to be 3/10. Probability of blue red, well, it's blue and then red given blue. So let's multiply the two, and we can come back over here and just see what we're multiplying. It's 2/5 times, you see it's blue red, so it's 2/5 times 3/4. So back over here, 2/5 times 3/4. And let's see, a nice cancellation occurs here, and this turns out to be 3/10. And then for the last one, the probabilities are right here on the chart. 2/5 times 1/4. 2/5 times 1/4. So back over here. And now a cancellation occurs here, and this turns out to be 1/10. It is interesting to notice and maybe to verify the validity of these in a fashion is to notice that these probabilities add to 1. And they have to do that. These are all of the possibilities involved in the situation. 3/10, 3/10, 3/10, that's 9/10, and 1/10, that's 10/10, or 1 for the sum of the probabilities. In making tree diagrams, in order to tell the number of items in the sample space, all we need to do is count the items at the ends of the branches of the tree diagram. Now, recall the situation where we flipped a coin and rolled a die. We just count the number of items at the end, and we found that to be 12. Well, think about it this way. In tossing a coin, there are two possibilities. There are two possible outcomes. In rolling a die, there are 6 possible outcomes. 2 times 6 is 12. Now, this idea can be used. Just multiplying the possibilities at each stage of the game gives us a way of counting. Now, sometimes this is called the fundamental counting principle or the multiplication principle of counting, something like that. But at any rate, it's the notion of multiplying options at each stage of the game. Consider this problem. How many 3-digit area codes are possible if the first digit of this 3-digit area code cannot be 0 or 1 and the last digit cannot be 0? Well, we have a 3-digit area code, and all we do is just place a blank for each of the possible digits in the area code. Now let's just think about choices. Now, how many digits are there? There are 10 of them. If the first digit, though, cannot be 0 or 1, then this first digit, we have only 8 choices for that digit. For the next digit, how many choices do we have? Well, there are no restrictions for the second digit, so there are 10 possibilities. For the last digit cannot be a 0, so there are 9 possibilities. So multiplying here, then there are 720 possibilities for area codes. There are 720 possible area codes given these restrictions. So all we're doing is multiplying the possibilities, the number of options that we have in each stage of the game. Here's another example. How many 3-letter words are possible? Now, by a 3-letter word, I'm not limiting us. I'm putting words in quotations because I'm assuming that AAA is a word, you see. So even though we don't have vowels or do have all vowels or whatever, they're all words, okay? So 3-letter words. Well, let's see. 1, 2, 3 letters. What are our possibilities for the first letter? We can choose from any of the 26 letters of the alphabet, so we would have 26. For this one, 26. For this one, 26. And so multiplying 26 times 26 times 26, we would get 17,576. Now, what about if we were talking about the same idea but without replacement? Without replacement, that means if we use A as the first letter, we can't use A as the second letter. So ARA is not a word. We have to disallow that. Well, how can we disallow that in this circumstance? Well, let's talk about our possibilities. We have 3-letter words, and we have the entire alphabet at our disposal here, so it's 26, number of choices for this one. Now, once we've chosen a letter, though, and used it, we can't use that letter again. We're not, it is not an option for choice here. So the next number of items for choice is 25, and then after that, 24. So 26 times 25 times 24, or 15,600 for the number of 3-letter words without replacement. Here's another one, same idea. How many ways can 8 books be arranged on a shelf? Well, if we have 8 books, we have 8 positions, 8 positions for choices. I'm just going to write 8 blanks. And how many choices do we have for the first book? Well, if we're looking at our 8 books, we have 8 books to choose from. After we've placed that first book on a shelf, we only have 7 choices for the next book, and then 6 for the one after that, then 5, then 4, 3, 2, and 1 for the last choice. Well, this brings up an interesting situation. This idea of taking a number and multiplying times every counting number all the way down to 1 from that value that we start with is the notion of factorial. And this actually is 8 factorial that we have written up here. It is 8 times 7 times 6 times 4, 6 times 5 times 4 times 3 times 2 times 1. And it turns out that the value is 40,320 for 8 factorial. So the notion of factorial, and it's the notation for factorial is the exclamation point. And we'll be using factorials quite a bit. Here's a variation on the same theme. Suppose we have 8 books, but there's only room for 3 books on a shelf. How many arrangements are possible? How many arrangements of 3 books are there if we're choosing from 8 books? We're taking 8 books and we're arranging only 3 of them. Now, how many different arrangements are there? Well, we again multiply our choices. It is simply, let's see, for the first book we have 8 items to choose from, and then for the second we have 7 and then 6. 8 times 7 times 6, 336 arrangements are possible. Now, all of what we've been talking about is the notion mathematically of permutation. The idea of permutation, when we talk about permutations, order is important. And whether we have importance of order or not is going to be important for us to determine when we make calculations about permutations. We're going to go on with another discussion in just a little bit about combinations. But to be able to recognize and determine whether a problem involves permutation or combination, we're going to test to see if order is important. If order is important, it's a permutation. If order is not important, it's going to be a combination. Now, in order to pick off whether or not order is important, often in this kind of problem the word arrangement is used. How many arrangements of those books are possible, you see? So how many arrangements of numbers are possible to give those area codes? All of those different arrangements imply that order is important and leads us to the notion of permutation. There's actually a formula associated with the notion of permutation. Here is that formula. Notice it involves factorial. And the notation for permutation is this, and there are a couple of options here. This is the permutation of n things taken r at a time. For the 8 books, 3 on a shelf, it's 8 books and we're selecting 3, or we're arranging 3 at a time. So that's the idea of the placement of these two. The notation could also be the permutation of n things taken r at a time, written like this. Interchangeable parts here. Now notice that in the formula, it's the n here, the number of items you have factorial, over the number of items you have minus the r at a time. How many at a time are you taking? You subtract that here and take the factorial of that difference. Let's use the formula here in this previous problem. In fact, let's use the formula in both of these two problems. First, for this one, if we're thinking about it as a permutation formula kind of problem, it's n things taken r at a time. For this purpose, it is, well, I'll tell you what we ought to do. We should, when you use the permutation formula, write it down just like you normally do with other formulas. You should write n factorial over n minus r factorial. And then we're talking about the permutation of 8 things taken 3 at a time. So it is 8 factorial over 8 minus 3 factorial. Now 8 factorial means 8 times 7 times 6 times 5 all the way down to 1. 8 minus 3 is 5 factorial. Now let me put this denominator here. I'm just going to show you a little shortcut that you can take from time to time. 8 minus 3 is 5, so this is going to be 5 factorial. Now when you begin to write the numbers in the numerator, this is 8 times 7 times 6 times 5, and when you get to 5 you can stop, because you can just call this 5 factorial. Instead of writing 5 times 4 times 3 times 2 times 1, it's 5 factorial, and so we have a cancellation opportunity here. So we have 8 times 7 times 6. 8 times 7 times 6, that's exactly what we had up here. You see, so we're really multiplying the same digits to get the same results. You would kind of expect that. All right, on this one, if we're using the permutation formula, we're talking about, gee, we have 8 things, but we're arranging all 8 of them. So it is the notion that it is, and the formula once again is n factorial over n minus r factorial. All right, so for this problem, it is the permutations of 8 things taken 8 at a time. So we're arranging all 8 items. So it's 8 factorial over 8 minus 8 factorial. Now in the denominator, we have 0 factorial. And this is a special definition in the factorial world, that 0 factorial is defined to be 1. So this is 8 factorial over 1, and the 8 factorial is just what we had up here. So the importance right here is the 0 factorial is defined to be 1. Permutations and factorials can be calculated using the calculator. On the TI-83, we would press the button marked Math, and this is the menu that shows up. We would like to be in this area, in the probability area, so we'll cursor to the right and then cursor down. Now notice the items that we're looking for. Here's the permutation calculation, and here's factorial. Let's use factorial first. we will access factorial when we enter a number, and here's the way we do it. We are going to go back to a main screen, and I'll find, let's say, 25 factorial. Now I want to take the factorial of 25, so I'll go Math, and then cursor to the right, and then item number 4, and 25 factorial, I'm pressing enter again, is this number. Now notice it is in scientific notation, and it's because we have 25. You see, this e means times 10 to the 25th power, so we would have to slide this decimal point 25 places to the right in order to get the exact value of 25 factorial. Factorial numbers can get awfully big awfully fast. Well, let's talk about the permutation idea. If we calculate the permutation of 8 things taken 3 at a time, which we were looking at just a moment ago on the board, then we would enter the 8 and then go to the Math menu, cursor over to the right, down to the permutation of n things taken r at a time, press enter, and now we want 3. You see, so it's the n is the 8 and the r is the 3, you see, and we enter the 8 first and then the permutation notation and then the 3 and then press enter to give 336 as we expected and as we found earlier on the board. Suppose we go back to the example of having 8 books, but this time, how many groups of 3 are possible? Now, not how many arrangements of 3 out of the 8, but how many groups of 3 are possible. Now, if we're talking about 8 books, and consider 3 of the books. Think about Treasure Island, Swiss Family Robinson, and say Tom Sawyer. Now, if they're arranged like this, Treasure Island, Swiss Family Robinson, Tom Sawyer, if I put Tom Sawyer over here and Treasure Island over there, it's a different arrangement, but it's the same group. You see, so this isn't the same thing as just taking 8 times 7 and multiplying times 6. So it's not just using that counting principle that we were talking about, that multiplication idea. We have to actually use a formula here. And this kind of situation is called a combination. And in the combination situation, order is not important. Order is not important. Often the word group or the word committee will be used in this situation. But the formula for calculating combination is very similar to the formula for calculating permutation. Here's the formula, and notice the notation, and I'm using the n things taken r at a time with both the n and the r on the same side of the c. Another way to illustrate that, or another notation that is appropriate, is the n combination of n things taken r at a time like this. And another way to note this, another notation, is n things taken r at a time like this in parentheses. Well, at any rate, the difference in the formula for combination and the formula for permutation is this r factorial in the denominator. And this is just in this formula for combinations to divide out those duplications that we were talking about in this problem. Now, back over here then, to solve this problem, we would begin by beginning with writing the formula. And then fill in information into the formula. Notice I'm changing the notation back and forth just so we'll be familiar with both. N factorial, that's the number of items that we have. And I should actually write the numbers for the n and the r here. We're talking about 8 things taken 3 at a time. So we're talking about 8 factorial over 8 minus 3 factorial times 3 factorial. So now it's one of those things, it's a manipulation problem from here. It's 8 times 7 times 6 times 5 and so on all the way down. Actually, we can take a little bit of a shortcut here by saying 8 times 7 times 6 times 5 factorial. And I know we can do that because 8 minus 3 is 5 factorial. and then here we have 3 factorial. So the 5 factorials can go out, same factors involved in both of those, you see. 3 factorial is 3 times 2, that's 6. We get a cancellation opportunity here. But at any rate, we end up with 56 as the number of groups of 3 that can be taken out of 8. Let me show you a shortcut. Before we leave this problem, I'd like to show you a shortcut right here that instead of writing what we wrote, we can take this kind of tactic. And it is to say that in the numerator will be composed of, you see, if it's 8 things taken 3 at a time, the numerator can be thought of as being composed of 3 factors starting with 8. So we can go 8 times 7 times 6. And the denominator is simply the 3 factorial. So this is 3 times 2. You see now this is 6, that's 6. They go out 8 times 7, 56. So either way you do it is fine. This is just a little trick, a little shortcut trick to deal with combination formulas by hand, sort of, if we're doing the manipulation ourselves. We'll look at the calculator on this in just a few minutes because that's probably the fastest way to deal with this. Here's another problem involving a combination. How many different 5-person committees are possible from a class of 20 students? 5-person committees from a class of 20 students. Well, we know it's a combination because we're talking about committees, groups. Order is not important. So we would immediately go to the idea of the combination of n things taken r at a time is n factorial over n minus r factorial times r factorial. And for our problem, it's the combination of 20 things taken 5 at a time. Notice the different notation, which is 20 factorial over 20 minus 5 factorial times 5 factorial. Now the shortcut here is to say, well, in the numerator we're going to have 5 factors starting with 20. So we could write this then as 20 times 19, 18, that's 3 factors. Here's 4 factors, here's 5 factors. So 5 factors starting with 20. In the denominator we have 5 factorial. And now when the smoke clears on all of this, it turns out to be 15,504 groups of 5, committees of 5 that can be taken from 20 students. Let's use the calculator to determine the number of 5-person committees that are possible from a class of 20 students. We have 20 students or 20 items. We want to take that 5 at a time as a combination. So we enter 20, press math, then over to probability, and then down to combinations, press enter, and then 5. Now notice again, as we found earlier, that the idea is that the 20 is the n things and the 5 is the r at a time. So they are on their respective sides of the combination notation. Pressing enter, we find that number to be 15,504 as expected. In the Colorado State Lotto game, there are 42 numbers. Players choose any 6. Then the state selects 6 of the numbers at random. The winning tickets are those on which the player's 6 numbers match the state's 6 numbers. The A part of the question is, from 42 numbers, how many groups of 6 are possible? And how many groups of 6 are possible? Notice the word groups implies that we're not interested in the order in which the numbers are chosen, just whether or not we have a group, kind of like a committee idea. So we have a combination notion here, and we use the combination formula which is given here. Now for our problem, it's the combination of 42 items taken 6 at a time, which is 42 factorial over 42 minus 6 factorial times 6 factorial. And the shortcut, as we looked at earlier, would mean this, that in the numerator we'll have 6 items, 6 factors starting with 42. So we would write 42 times 41 times 40 times 39 times 38 times 37. In the denominator we have 6 factorial, which is 6 times 5 times 4 times 3 times 2. And then when the smoke clears on the cancellations, we find that that total number is 5,245,786. Quite a lot of groups of 6 that are possible from just 42 numbers. The next part of the problem says, if you buy one lottery ticket, what is the probability of winning the grand prize? Bear in mind that this many groups of 6 are possible. So when we talk about favorable outcomes over possible outcomes, this 5 million some odd number represents the number of possible outcomes. So, and we've got only one ticket, so the probability of winning is 1 over that 5,245,786, which turns out to be this very long decimal. Notice how close this decimal number is to 0. 0 would imply that you cannot win. This number is extremely close to 0. Now, let's change the problem a little bit. What if you buy 10 lottery tickets? Now what is the probability of winning the grand prize? Maybe it's increased a great deal. Well, let's see. The probability of winning then, favorable outcomes, we have 10 tickets. So it'd be 10 over that 5 million number. And when we divide this out, all we're doing is eliminating one of the zeros to the right of the decimal point. It really doesn't change the probability that much. It doesn't give us the inside track in winning the lotto just because we've bought 10 tickets, you see. This number is still very close to 0.